Please, Deanne.
Okay, yes, so I'm Deanne Coppejans. I'm from South Africa. I did my undergraduate degrees in physics and theoretical physics in South Africa, and then my MSc astronomy in South Africa as well. And then I did my PhD astrophysics in the Netherlands in Nijmegen. And I worked a lot on cataclysmic variables over that time. And now I'm in the United States as a postdoctoral researcher. I'm at Northwestern University, so it's just north of Chicago. So now I'm, as well as cataclysmic variables, I'm working on all kinds of explosive transients, supernovae, neutron star mergers, anything explosive is interesting. Okay, so if you have a question or if I accidentally use some jargon that you don't know, please just feel free to answer questions while I'm talking. Yes. Okay. So in this talk, I'm going to tell you about what are cataclysmic variables or CVs, and then what are dwarf novae, and what we can learn from dwarf novae, and in particular why the dwarf nova SS Cygni is very interesting. And then moving on to my specific research, I'll discuss whether or not these dwarf novae launch powerful collimated flows of matter out into space, because that's a big outstanding question in the field right now. And then I'll just end off telling you about some ongoing research and future work. Okay, so for the first thing, so for those of you who do photometry of variable stars, you'll know that when you take observations of a cataclysmic variable, you'll get an image like this. Are you seeing my pointer? Can you see where I'm pointing with the mouse?
Yes.
Yes.
Okay, great. So this little fuzzy blob over here is a cataclysmic variable. And I observed this with a telescope in South Africa. It's a 2-meter diameter mirror, and that's what we saw. But the very interesting thing comes in when you see how call a light curve. So then you get beautiful light curves like these ones. Here's brightness changing over time, and they show these very deep dips in brightness. Or you get other cataclysmic variables that show these shallow, broad dips. And you always see a lot of like flickering and murmuring when you see cataclysmic variables. So what are we actually seeing here? Well, this is just a diagram I made of a cataclysmic variable star. It consists of a white dwarf and another star, and they are orbiting each other. But they are so close that the white dwarf is pulling lots of material off the secondary star. So it's actually eating this secondary star, and it distorts it into this weird teardrop shape. So you've got this double star system going around on a matter of a few hours. So when the material is pulled from the companion star, it streams down towards the white dwarf, and then it collides with other material from before, and it spirals down, and it forms what we call an accretion disk. So all this material around the white dwarf is busy falling onto the white dwarf as it spirals inwards. So are there any questions thus far?
What does L1 stands for? Is it the Lagrange point? Or?
Yes, it's the Lagrange point. So that's the point gravitationally where the matter from the secondary star can leave and move on to the white dwarf. Okay, I'll move on then. So what are we seeing in these light curves when we actually observe it and see a change in brightness over time? Well, this particular CV, you see it's the same brightness and then it shows a sudden drop. what happens here is that the one star is moved in front of the other star. So it's blocking some of the light. So you see a sudden drop in the light as it moves in front of the other star. This one's just another example where maybe the stars are not aligned 90 degrees to you, so there's a slight offset, so it blocks part of the light of the other star as it moves around. Then all this flickering and flaring that we see is because mass is not transferred smoothly from the star. So you get like blobs and things coming down into the star, and you've got it colliding with other material in the disk, so you see flickering. So these are all variability that we see on timescales of a few hours or a few minutes. But there's one thing that we see happens over weeks to months that's very interesting. And this is the dwarf nova outburst. Yes. There was a question? Okay. So some cataclysmic variables show what I'm going to describe now. So they're flat and faint for a very long time, and then suddenly they increase in brightness by a factor of up to 100. Just over one day, they increase by a factor 100 brightness. And then they stay up there for about a week, and then they fade away again. And this will happen every few weeks to months, depending on which system. And this is called a dwarf nova outburst. So if you see here, here's a long-term light curve of S Cygni, a cataclysmic variable that shows these. And this is from the AAVSO. And this is a 100-year light curve. It's beautiful. But you see every few weeks to months, you get this jump in brightness. Okay, so cataclysmic variables that show these dwarf nova outbursts are called dwarf novae. So what are we physically seeing here? Well, we've got all the material coming in from the star, and it falls down towards the white dwarf, but the matter comes in faster than matter in this disk can fall onto the white dwarf. So over time, there's more and more material in the disk. It becomes denser and denser. And it reaches a point where the disk can't hold any more matter in its current state. And then there's an instability that switches the disk from a cool, low density, from a cool state to a bright, hot state. And that is the dwarf nova outburst. So if we look at this during the faint state, you've got a cool disk, and then this instability happens and it becomes bright and hot. And this is the dwarf nova outburst. So the increase in light is just the accretion disk brightening. And over time, all the matter drains out of the disk, it collects on the white dwarf, and the density goes down, and the light from the disk drops. So all you're seeing in dwarf novae is a switch between a bright, hot disk and a cool disk.
A question.
Yes.
What material is dragged to the white dwarf? Is it mostly hydrogen, only hydrogen, or anything else?
It's mostly hydrogen, almost completely hydrogen.
And in the disk as well, then?
Yes.
Okay.
Hernan, you had a hand up.
Yes, I had a question, but yeah. In this diagram you're showing now, it's a kind of a cartoon about the star on the accretion disk. Are there cases where the accretion disk grows so large, or if the stars are too close to each other, then the accretion disk more or less embraces both stars at the same time? Are there such cases, or the cartoon you are showing is closer to what we think is the real situation?
Yeah, so the cartoon is closer. If the disk gets too big, you get gravitational interactions with this donor star. So there are forces that keep the disk smaller.
Yeah. Okay. Thank you.
So I got a question too. Is that the accretion disk? So the accretion just changes, right? So the state that it is in changes into another state where it emits light. So what process are we talking about here? What are the states and what is the transition between the states?
So as material builds up in the disk, you get more, and it gets warmer because you've got more material and there's viscous heating going on. And it reaches, so the temperature increases over time. And at some point it reaches a temperature where the hydrogen in the disk becomes partially ionized. So there's enough energy that the electrons and positrons separate. And in that state, there's an instability where all further energy, well, it's better at keeping the energy in. So it gets hotter very suddenly. So in the hot state, you have all the hydrogen is ionized and the disk is very hot. But in the cool state, none of the hydrogen is ionized. Sorry, I know that was a bit technical. I hope that answered your question.
Yeah, no, but you're on the way, so thanks.
Okay. So dwarf mode.
Sorry, I have another question. May I? Can we go back to the? I am sure if the cartoon is realistic depiction of what we think is a real situation with the disk being comparatively small in comparison to the secondary star. What happens if we have a dwarf nova that is aligned in such a way that we can observe an eclipse of the secondary star, of the primary star by the secondary star during an outburst? Is that possible? Because my understanding is very confused about this. What do you have to say about that?
Yes, so we do see eclipses during outbursts as well.
Ah, okay. Okay.
Because those stars are still orbiting, so we still get the blocking of the light.
Yeah, okay.
Yeah.
Thank you.
Sure. Okay. So why are these dwarf novae interesting? This whole process that I've described to you, we have quite a few questions about it. So we see some dwarf nova outbursts that are a little bit different or show little brightenings beforehand. I won't get into all the questions, but we have a lot of questions about this physical process. And we have these same questions in other types of systems that are similar, where you've got either a white dwarf or a neutron star or a black hole, all compact, very dense stars that are pulling material off a companion star. So for example, we have X-ray binaries. This is a neutron star or black hole pulling material off another star. And even up to the size of whole galaxies. So this is a supermassive black hole pulling material into a disk around it before it settles into the black hole. So this process is common to lots of different objects. And dwarf novae, there's lots of them and they're nearby and they're comparatively light. So general relativistic effects are not such a big problem. My summary is just that it's easier to study these processes in cataclysmic variable stars. So my main science question in this field is, what is the physics of jets? Now, jets, if you look in both these images, you've got the stream of material that is being spun up a large fraction of the speed of light. It's very high energy, very bright. and it's a very narrow stream of matter. You can think of it like water from a fireman's hose, really fast and energetic. So there's a lot we don't understand about how these jets are launched, what makes them so narrow. And a big question is whether these cataclysmic variable stars show these jets of matter, whether they're able to do this. And as of today, we don't have a firm answer. We don't know. So that is my main research question in this field, and I'll tell you a little bit more about it now. Okay, so I'm going to start with saying, how do we actually look for jets? Okay, so there's a lot of light. The electromagnetic spectrum is really broad. If we look up here, the lights, the colors of light that we see are only this tiny fraction of all the light that's out there. If we get more energetic light, we move up to ultraviolet and X-rays. And if we move to less energetic, we go all the way down to radio waves. So this is what we see with our eyes, but jets make light in this region here at radio wavelengths. These are like the wavelengths that your microwaves to cook food uses to cook food, or the wavelength that your cell phones communicate in. And we need different types of telescopes to observe light from these wavelengths. So this is just a picture of a telescope I use a lot called the Very Large Array. It's in the United States. And these dishes are 27 meters across. I've actually climbed up there and stood on one of them. They're amazing. And they're all on a little railway line, so we can move them. And the distance between dishes is, I think it's on the order of 15 kilometers. It's a big telescope. But when we look at jets with these kind of telescopes at radio wavelengths, we see beautiful structures like this. This is an image. That little dot in there is an entire galaxy, the whole Milky Way, for example. And it's ascending off these thin streams, jets of matter into space, and they're colliding with all the dust out there and making these big plumes of energetic light. So just as a side note, this particular 7 kilometers away from us, and from here to there is 10 to the power 16 kilometers long. These are huge structures. So that's just an example of what a jet can look like in radio. So the summary is, I need to look at with radio data to see these jets. But a big problem was that we looked for cataclysmic variables in the radio, and we just didn't find them for decades. And so people concluded that since we didn't see the jets at radio wavelengths, they aren't jets. And so for many decades, we've been saying CVs don't launch jets, so the environment of CVs is not capable of doing that. And we've been using that to put limits on the physics of jets. And then we reached 2008. That's when my supervisor in the Netherlands, Elmar Kerding, did a very, very, very careful comparison between cataclysmic variables and the other systems like it that do launch jets. And he realized we were looking at the wrong time for the jets. So if you just look at these light gray points, you'll see that's the dwarf nova outbursts. These data were actually taken by the AEVSO. And what he said is that just after the beginning of outbursts, we should see a bright flare of radio emission from a jet. And after that, the radio emission should go back to nothing again. So we all our observations in the previous decades were taken at the wrong time. And sure enough, he went and he observed the dwarf nova SS Cygni, and he found this bright flare. And him and several other authors after that concluded that this is a sign that CVs actually do launch these jets of material. So this turned the field on its head for a while, because we've been assuming that cataclysmic variables do not launch these jets and using them to study jet physics. But the problem at this point was that we did see a flare of radio emission, and it was at the right time, but it's not conclusively a jet. We could be seeing something else. So what we actually needed, it could be completely certain that they are there. So you're probably imagining that beautiful image of a jet I showed you earlier. This is our best image of a CV. Okay, so for those of you who observe, usually the resolution you get in optical images is on the order of 1 arcsecond. This is 1,000 times better resolution than that. And still we only see 2 little blobs. This is SS Cygni, and this is potentially a jet. I say potentially because there were some difficulties with the data. It's not very clear that that's a real blob. So the summary is that SS Cygni might have a jet. It's likely that it is a jet, but we don't know yet. And this is where I came into the story with my PhD. I am going to pause for questions now, if you have any questions.
May I ask?
Yes.
Yeah. So we are quite clear what we are talking about. You are talking about the white dwarf now, the jets from the white dwarf,
Yes.
and nothing else. Thank you. Okay, satisfied.
I see there was another question, but
Nance, got a question?
Yes, I have a question. Is this map image you are showing? I guess it's a reconstruction of data from some kind of model or measurement. But is this aligned to the north? I mean, is aligned to the right ascension and the declination axis? Oh, okay.
Yes. So this is right ascension and declination. Usually, it's just the way we do it. We make north to the top and east to the left.
Yes.
But yes, it's
yes.
right ascension and declination you're looking at.
And you can't correlate the blob to the east with an existing star or any other visible
Yeah,
object.
there's nothing else there. If it's real, then it is part of SS Cygni.
Ah, okay.
The big question is whether it's real.
Okay, thanks.
Okay.
Yeah, one question also. That is the jet that you may be seeing there, yeah. But what about the disk? Is it all too small to be seen, or could it be seen in other wavelengths? Or
yeah, it's too small. It's too small to actually see on this with this resolution.
Yeah. Okay.
Cool. Gustav also raised a hand.
Yes.
But a physical hand. Yes.
Yes, I have a question, maybe a bit out of the field, left hand, but still, I mean, we have these dwarf nova phenomena, SS Cygni going off every 5th week or something like that. But then there's also the phenomena of stars like Z Cabellapardalis or RX Andromedae, that they go off and then they have a standstill for half a year, 1 year or 2 years, they don't do anything. They just sit still and then resume activity. What's the current explanation of that? Why do they do that?
So the current explanation is that the mass transfer rate from the star is almost high enough to keep the disk in this very hot state. So essentially these objects are their disks are staying in this very hot state. And then with a very slight drop of the mass transfer rate from this donor star, that allows the disk to drop into a faint state again. But the summary is there's enough mass being transferred from the secondary star to keep the disk hot for very, very long periods of time.
Thank you.
Johan has a hand raised.
I'm just going to turn the volume up.
Yeah. No.
Yes, I have a question. I was looking at, I was wondering about this picture, the radio picture of SS Cygni. You say the left blob is an indication of a possible jet.
Mm-hmm.
But there must be some kind of symmetry here with jets going in two directions at the same time. So why are you not seeing another blob? Is it because there is some problem with red or blue shift, or is there some obscuration of other material in the system, or what is the reason?
So there could be several reasons there. There's an effect where jets pointing towards you are brighter. It's a general relativistic effect, but the summary is if the other jet is pointed away from us, it will look fainter. But there's also the chance that maybe there's not as much material. Well, maybe the other jet is not as bright because it's not hitting enough material out there, or maybe it's just a resolution problem. So with radio telescopes, what you see on the image is very dependent on how far the dishes are apart from each other. Resolution. So maybe it's just because of that. The other possibility is
you're basically missing some. Possibly you're missing some information at some spatial scale here because of the distance between the telescopes. Okay.
Yeah, precisely.
Yeah. Okay. Thanks.
Okay, can I continue, or are there more questions?
Go ahead. We don't have any more questions for the moment, I think.
Okay, so this was the state when I started my PhD. We had one CV that was maybe launching a jet. So the next step was I started looking at other CVs at radio wavelengths to see if we could find them in other systems. Oh, I should start by saying, so the implications of this is all the jet models we constrained using CVs, assuming they weren't launching jets, were called a little into question. And CVs are nearby and bright. They'd be really good targets to study jet physics with. But at this point, we only knew of SS Cygni. We still didn't understand why we weren't seeing other CVs at radio wavelengths. So I just want to explain to you why amateur astronomers have been so amazing to this field. So this is, again, the light curve in gray of a dwarf nova outburst, and SS Cygni showing the bright radio flare. So this bright radio flare occurs within 1 to 2 days of the dwarf nova outburst starting. It's very quick. And in many systems, in fact, in almost all dwarf novae, we can't exactly say when a dwarf nova is going to start. We know it's going to start within these few days approximately, but we don't have an exact time. So to, okay, and picture of, there are only 3 or 4 in the whole world that I can use, and they cost on the order of $100,000 a night to run. So observations are very competitive. We have to write observing proposals, and then the best ones get chosen. My summary is that you can really only get a few hours on a radio telescope. So I can't just sit there and observe it for several months. I have to tell them exactly when I want the observations done. So what we did was we ran a campaign with the AVSO, where amateur astronomers across the globe would monitor a bunch of different CVs and tell us when they started the outburst, so that we could then go and take the radio observations. So that worked really well. My thesis was, my main thesis result was largely thanks to all the great observations from amateur astronomers. So with this campaign, we actually observed a system of 9 CVs, and I proved that they are actually producing radio emission. Our observations we taken in the years before were taken when radio telescopes were not as sensitive. So we just weren't detecting the emission, and we were also observing at the wrong time. So that was a big shift in the field. And there's a lot in this figure, but just focus on the fact that here again in gray is the dwarf nova outburst. The open data points are the radio emission from this SS Cygni, and the closed, filled data points are the ones that I took of a bunch of other dwarf novae. And we didn't find that radio flare right at the beginning of the outburst that is supposed to come from a jet. We didn't find it in any of them. But the one problem was that we take an hour observation and 2 days later come back for another 1 hour observation, because the radio telescope time is so valuable, we can't just sit and observe it for a while. So there's a chance that there was a flare in between. It's not certain yet, but a lot of the other properties of this radio emission that we saw were consistent with the jet. So these observations didn't rule them out, and they didn't prove that they were jets either. So steps to answer this question. Well, obviously the first thing is to get more frequent radio observations at the beginning of a bunch of different dwarf nova outbursts, so that we can actually conclusively say whether all dwarf novae show this radio flare from a jet or not. The other thing is we need more of these high spatial resolution images to try and see the jet. And again, we need to run campaigns with amateur observers to trigger these observations at the right time. So we need telescopes the size of continents. So here's one in Europe, there's one in North America. We need these huge telescopes to get that high resolution imaging. The other thing is there's a lot of light telling us different things about the CV. So the radio tells us about the jet. The optical mainly tells us about the disk. Then you've got ultraviolet and X-rays that tell us more about the white dwarf. So what we need is more observations with more of the spectrum of light to fully understand what's happening. And the final thing is we need to use all these observations to prove that it's a jet and rule out other mechanisms that can make radio emissions. So it's looking very likely that it's a jet, but at the moment I can't rule out maybe there's a flare, like a solar flare in the donor star, or maybe there's interactions in the disks making this radio emission. So these are the questions that need to be answered and the observations that need to be taken in the next few years. And there's some really exciting developments that mean we might be able to answer this question within the next decade. And one is that the Square Kilometre Array, that's a huge radio telescope that will span South Africa and Southern Africa, as well as Australia. Europe are key players in this field. This will be the biggest telescope ever made. If you add up each individual telescope, the area of that, it will be 1 square kilometre. That's why it's named. So it'll be really sensitive, have really good resolution. But the precursor telescope where we're testing all the technology to make this has already been built in South Africa. So it's called Meerkat. And we've got an optical telescope that looks an exact on radio light curves and optical light curves, so we can examine this process in detail. And I'm part of a team that has been given many hundreds of hours to try and answer the science question. This is just our logo. This is Thundercat team. So in conclusion, one of the biggest questions in the field is whether CVs launch these jets, because they can help us understand jets and all kinds of similar objects. And in the next few years, we've got new telescopes that we can use to do this work. And in the future, we're going to have many more campaigns with amateur astronomers to help get the observations at the right time. So thank you for all your observations. They really make a big difference in science. It's great working with you all. And thank you. I'm happy to answer any questions.
Thank you. Thank you very much. We got a question by Herman.
Yes, I have too many questions. I'm sorry. Yes, my first question is, so you are planning, we are now writing proposals for when the time this new telescope is built, or are you hoping to use soon other existing telescope to start a new campaign on SS Cygni? And my other question is, if you consider that when you, it's very nice the idea to amateur and professional astronomers collaborate, but we amateurs are possibly more constrained in terms of the seasons when we can observe these stars, because we depend that they are not too low on the horizon, possibly, or they are in general well located for us. So is this something you consider when you plan those collaborations? Thank you.
Yes, so for your first question, I'm working, at the moment, I haven't written a proposal for this science. I'm also working on other projects. But this telescope in South Africa, we're actively doing observations there. And I am planning to run a new campaign on a bunch of dwarf novae, maybe in the next year or two. I just need to finish some other projects first.
Good.
For your second question, yes, so that's actually one of the advantages with working with amateur astronomers, because they're all over the globe. So if the one telescope we have access to, it's cloudy or it's just a string of bad weather, it's not so much of a problem. For these campaigns, I work out which dwarf novae will be visible in the time span that we want to do the observations.
Okay, thank you.
Great. Johan is next.
Yes, I think it was your very first slide, Jan. You showed in the low state, these cataclysmic variables have flickering light curves, and What is the knowledge of the reason for this? You mentioned something about that, but can you go into some more detail? Is it optically thin gas in the stream, for example, which is with varying densities of temperatures, or is it optically thick gas in the disk, so you have obscurations and things like that, or what is going on?
Yeah, so we do have like blobs of material. So there's the optically thin and optically thick pieces in the stream.
Okay.
That's some of the flickering. And then they collide with the disk and they make a sort of a brighter area where they slam into the other material. So there's a lot of flickering as it hits the disk.
Mm-hmm.
And then even in the disk, you can have instabilities where you, sorry, I'm just trying to think how to explain this. Where you've got instability, so you've got material showing waves in the disk and effects like that that can produce this flickering emission.
Okay. Do you see some kind of periodicity in this pattern?
So some of them we do. So we have, sorry. So some of them we do see periodicities, and we call those quasi-periodic oscillations, or QPOs, or Dvärgnovor oscillations, DNOs. You might be familiar with that terminology. So some of them do show periodicities, and those are mainly the ones that have oscillations in the disk, because those oscillations are periodic, and as they go around the disk, they're periodic as well.
So are there like waves forming in the disk, or is it or spiral patterns, or what kind of oscillations are you talking about?
You can think of them as density variations. There are some models that show the waves that like increase in height over time as they move through the. Say if you can get a spiral density wave, as you said, in the disk, and that can produce some of this behavior. So there's still a lot of ongoing research in that, but it's definitely the disk that is making these variations.
Yeah. Then I think if I have a final question. You have been talking about radio telescopes here. What about the new era of very large optical telescopes like the ELT? Can they contribute to this picture as well?
Yes, they can. So there's quite a lot of things that can contribute. So one of them, for example, is they'll be much more sensitive, so we can pick out these oscillations much more clearly. So for example, here you'll see that these are dots on the light curve. It's little integration times. We can't do continuous observations, but with bigger telescopes, we can do finer sampling in time. We can really get down into the statistics there. Also, one of the big things is what happens to cataclysmic variables. So in their lifetime, they start at a certain distance from each other, and over time they slowly come closer to each other as they release. Let me just say they slowly come closer to each other, and at some point it reaches the phase where they become very, very, very faint. So finding these faint cataclysmic variables, i.e. the very old ones, is important to understand how they evolve. And these big telescopes will help with that.
Okay, thanks.
Sure.
I think we got Bengt.
Yeah, some more question just on the disk. I was wondering how small is it really? Is it possible to take any picture of the disk itself, or of the two stars, or how are they so very small?
So the whole cataclysmic variable is about 10 to the power 11 centimeters. That's the scale we're looking at. And the disk is maybe a factor 10 smaller, so maybe around 10 to the...
So a tenth of the whole system.
Yes, yes. So those are the size scales. So at the moment, we can't resolve that, unfortunately.
Not even with bigger, newer telescopes like James Webb or...
There's a potential maybe with some optical interferometers, which is like 2 optical telescopes joined together. I don't actually know the resolution of those though, so I'm afraid I can't answer that question. There's a potential, but I think it'll be very hard or impossible.
It's very small and impossible almost.
Yeah.
Okay.
Oh, great. Hernan, I think so Johan still have your hand up and Bengt have your hand up, and then Hernan, I think it's your turn, Hernan, right?
No, I'm sorry. I just forgot to lower the hand. Sorry. Yeah, okay. Sorry.
Yeah. So then I'm sitting on 2 questions at least. But first of all, these jets. So what is the process that? What's it behind them? Why are the jets emitted? What is the process? Because it's high energy. So what is it that triggers this jet?
So you've asked the golden question.
Okay, so and now you get the answer.
Yes. So the models, at least, we probably understand the jets from black holes the best. Mm-hmm. So the main model there is that we've got magnetic fields and material in the disk that help to spin up this material and accelerate it away from the system. So the very precise details, I'm afraid I can't answer about, and we don't understand the full process. Yeah. That's one of the things with cataclysmic variables, because they don't have such strong magnetic fields. So if they're launching jets, then there needs to be another mechanism for launching jets, probably because of the material around on the disk helping to collimate this material away. That is the big question. I can tell you what makes a radio emission, if that's part of what you wanted to know.
Yeah.
So you've got all this material traveling away from the from the neutron star black hole, and it slams into material around it, just hydrogen in the surrounding environment. So you have all these shock waves forming, and in these shock waves you have electrons being accelerated to very, very high energies and spiraling along magnetic field lines. And that's making, we call it synchrotron emission. Mm-hmm. For the physicists listening, it's just higher energy cyclotron emission, essentially. Mm-hmm. So that's what we're seeing.
Cool. Yeah, but this jet, does it come from, because I was a little bit confused about that, is it from the white dwarf or is it from the accretion disk? Because
it's from the very inner accretion disk.
It is from
very close to the white dwarf. Yeah.
Yeah, because the whole outburst is about the dynamics and the physics of the disk, not of the star. Does the star play any role in this?
So there was a very long debate for many, many decades, because there was a competing theory that it was the secondary star going through some cycle and making more mass go through for a while. So that was disproven. But the more we investigated, we think there is some effect from the secondary in some systems. So the short answer is no, according to the traditional model, but recent research is indicating there might be some effects in some stars.
Yeah, cool. The whole thing is that these are very complex systems, very complex and very dynamic systems, and therefore also I think it's so exciting. I have another question that has to do with this corporation and the role that amateur astronomers can be, because you pointed to the importance of alerts about the outburst, right? But what other roles in relation to these cataclysmic variables can we play as amateurs? Where else are our observations potentially useful?
So I don't know if you've heard of Joe Patterson. Okay, well, he runs a organization called, I believe it's the Backyard Astronomers. So yeah, so they take very good long-term observations of cataclysmic variables, and there's a lot of questions we still have about the outbursts. So we know of a few thousand cataclysmic variables at this point. Sorry, something in my and we don't yet know how frequently they all go into outburst, or what the lengths of the outbursts are in all of them, or how they vary over time. So observing CVs long-term really, really helps with that. Also, we're still finding new CVs. So the three plots I'll show you here are from my master's project, where I was observing CVs and then doing time series analysis, even just to work out orbital periods. So amateur astronomers taking observations like this, I mean, this is maybe a bit too faint, but of CVs in general, to work out orbital periods and work out system properties is great.
Yeah. Great. Do we have any more questions or comments? Yeah, Gustav, go ahead. You're still muted, Gustav. You're still muted.
Can you hear me?
Yes, now we can hear you.
I have a question on the longer time scale. What's the difference between CVs and recurrent novae, like T Corona Borealis, for example, or U Scorpii, things that sort of explode once in a century or something like that? Are they the same phenomena, just on a longer time scale, or are they different beasts, so to speak?
They're different beasts. So the name is a little misleading. So what you're talking about is novae. So these are called dwarf novae, but they were named before we understood what was happening, so we thought it was a smaller version. But it's actually completely different physics. So in these systems, like the recurrent novae, that material is falling onto the white dwarf, and it builds up on the white dwarf to the point that you get a thermonuclear explosion. So what you're seeing there is an explosion on the surface of the white dwarf. So that's nothing to do with the disk. So most CVs show this nova. I think the current idea is that every CV shows one at some point. I think that's the current understanding. But the recurrent novae, because there's so much mass being transferred from this other star, the mass on the white dwarf builds up quickly enough that you see this explosion more regularly.
Thank you. So the explosion is on the white dwarf in itself. It's not on the accretion disk.
Yeah, it's the white dwarf itself.
Yeah, thanks.
But it's still an accretion disk. It's still a binary system, right?
Yes, it's still exactly the same system. Yeah. It's just that material piles up on the white dwarf itself and then has a thermonuclear explosion.
Right. Anand's got a hand up.
Yes. Thank you for the question, Gustav, because I think it's very interesting. I was always confused by that phenomenon. I always considered that dwarf novae and recurrent novae were some sort of family cousins. But thank you for the explanation. Now I have a different, similar, related question. in a recurrent novae, the thermonuclear explosion makes the whole accretion disk to blow up and disappear, in contrast to dwarf novae, where the accretion disk somehow stays forever or grows or whatever. Can you explain a bit on that?
Yeah, so in dwarf novae, the disk does stay and brightens in the dwarf nova. With recurrent nova, I'm not 100% sure what the current research says. I think there are at least some systems where the disk stays intact. I would expect the disk to stay intact. That's what I think.
Okay, but in the case of the dwarf novae, the disk is not severely affected by the outburst. It just brightens, it doesn't lose mass.
Yeah, it brightens and mass travels more quickly through the disk.
Okay.
So it does lose mass more quickly in that state. So the size of the disk changes a little bit and it loses some material, but the overall, yeah, the disk stays as a, okay, sorry, let me explain. Okay, yeah, the size does change a little bit and the temperature is different and the amount of the rate at which mass moves through the disk changes in the dwarf.
Good, thank you. And a last question. So over the time scale of maybe tens or hundreds of thousands of years, what happens with the mass balance of the disk? Does it grow or shrinks or stays more or less the same? What happens on the longer scales? I mean, a star like SS Cygni, we have outbursts every few weeks, but what happens to such a star on a scale of many thousands of years, up to 1 million, say?
On the long time scale, so the secondary star keeps on giving mass to the white dwarf.
Yes.
So so over time, there's less and smaller as it hands over its mass, and the system shrinks. So the disk shrinks as well over that very long time scale. Yes, and the amount of mass being transferred decreases, so you don't get as many dwarf nova outbursts. They become less frequent and the whole system fades.
So you may end up with the following situation, that the former secondary star has now been outstripped of its atmosphere and become a white dwarf itself. Is that possible?
Not quite a white dwarf, but you are right in that it becomes so small, it loses so much of its mass that it's not what it was before. Yes.
Thank you. Thank you for your answer. Now I'm shutting up, my colleagues.
Okay. Great. It's cool. Interesting with your questions, Anand. So more questions, more comments.
May I ask?
Yes.
Please, Deanne, can you tell us a little about yourself? Did you start as an amateur yourself? And which kind of astronomy did you work in your real young years?
So I was never actually an amateur astronomer. I always found science and reading about astronomy interesting. So I was particularly interested in black holes and things like that. So, but I'd never thought of it as a career until I saw this big new telescope that they were building in South Africa, and there were bursaries and things to train astronomers up. And it was only at that point that I started thinking of astrophysics as a career.
But
Before then, I was thinking,
that's in recent years, really, more or
yes.
less. Okay.
Yeah, so when I started studying physics, I actually wanted to do biophysics and do medical research. And then I saw this exciting new telescope and then I realized, oh, I can actually study black holes for a living.
Good. Can you tell us a little about, I mean, it's a curious question in this fantastic webinar. Thanks, Magnus. In what ways has the current situation with the coronavirus hampered your research? I mean, most of the telescopes in the world are closed down for the moment.
Yeah, so there's different fronts on that. So most of our work is computer work.
Okay.
So I've been able to continue with data that I already have, and all just working from home. We have a lot of Zoom meetings.
Yes.
A lot of Zoom meetings. We have had the problem where, so the group I'm in, we are interested in supernovae. So we've had very exciting supernovae going off, and most of the world's telescopes are down. So there've been some exciting systems we've missed. But having said that, we're finding more and more interesting supernovae, so we will catch up with that.
Okay, congratulations. Good luck.
Yeah,
Thank you.
You just recently published a paper on a new form of eruptive object as well, which sounds very interesting. Gustav is waving a hand. And you're muted, Gustav. You're muted.
I have a question about new telescope technologies. In the coming years, there are several telescopes coming online, such as the Vera Rubin facility, formerly known as the Large Synoptic Survey Telescope, something. I'm thinking about time domain astronomy, where you have, instead of a few amateurs watching the sky, you have these automatic telescopes surveying the sky each and every night. What do you think, if you're working on CVs, this type of variable stars, what will the outcome be in like 5 or 10 years of this new photometry surveys?
So do you mean from the perspective of amateur astronomers or for science?
Actually both, but I'm mostly interested in how it will affect science per se. What can you learn? I mean, will you be able to find new types of dwarf novae with these photometric surveys, and what can they do for you?
So there are a few different points there. So the Vera Rubin Observatory, they will be observing most of the sky, but only every few days. So they'll be more useful for looking at supernovae that change over long. We'll still learn a lot from that, because even observing every few days, if we have a lot of data, we can work out statistics like how bright most dwarf novae reach and on what timescales. There's a lot of science we can do there. But we won't be able to follow one dwarf nova and find out properties like the orbital period and stuff that like amateur astronomers could get from observing more frequently over a night. There are a lot of other large-scale surveys that are going on each night. None of them have the big field of view that the Vera Rubin Observatory will have. So they'll observe smaller patches of the sky, but more frequently. And we're finding a whole lot of new kinds of variable stars and supernova explosions. And it's actually at the point where we as astronomers can't even observe a fraction of them anymore. So like the Vera Rubin will observe tens of thousands of supernovae every year. So we're actually, as a community, now working on training algorithms, so artificial intelligence and machine learning, to help us go through the data and find interesting trends and spotting up interesting objects and studying whole populations of stars and classifying them. So the whole astronomical community is going through the shift right now where we can't cope with the amount of data coming in, and we're really working on our software to help process this all. But I should also say that there will always be a very key role for amateur observers. There are a lot of, so these big surveys are good for doing large scale population studies, but we're always going to want to go after a specific object that looks interesting and do big campaigns on it and figure out what the real physics is of that object, because you need to do both to make advances in astronomy.
I was participating in this AVSO online meeting just recently, and I listened to one presentation there about this algorithm, the machine learning, identifying different kinds of variable stars, and the problems in doing it, and sort of the work that remains in trying out and testing those for amateurs. And there was a woman, I don't remember her name, but she was teaching astronomy and had her students go through these light curves and the periods, and also because the periods suffer from the periodicity of the observations, right? So there are some kind of random artifacts in it. But there's sort of a niche in checking and testing and finding the correct periods and finding new variables in that. That was quite cool. Different way of working with this enormous amount of data, but on the computer. Cool. That was cool. Right, more questions, comments? No. So maybe we're at the end of this seminar, this webinar. So should we all give Deanne a hand, a round of applause? Can we do that? A Zoom applause?
Yeah. Thank you. Thank you very much.
Thank you very much, Deanne. And